Hi everybody, Dr. Waite here. This lecture video is for hydraulic engineering on Wednesday, the 14th of February. This is class 16, and as previously announced, this lecture video and the class meeting for Friday is also going to be posted on YouTube, so we won't have any in-person class meeting those days. You've just turned in homework number 5, which is the problem set that was related to applying the Hardy-Cross method to analyze a pipe network, and you also had a couple of questions on there related to water hammer and surge tanks. So your next assignment, homework number 6, is available now on Blackboard. You can download that, and it should be submitted before class on Wednesday, the 21st of February. Also that same day, we're going to have our first midterm exam, and the equation sheet for the midterm exam is posted online, so you don't need to prepare any kind of a formula sheet. That will be provided for the test. The other thing I wanted to remind you is that for Monday's class, for class that we're going to have on Monday, the 19th of February, you need to come to class with your laptop and water gems installed. So please make every effort to get that installed and activated and ready to use on the class day, because if you come to class without it working, then you're not going to get much out of that class meeting. Today's lecture video is related to pumps. We're going to be doing another example related to finding the operating point when we have a system curve and a pump curve, and we're also going to be talking about the issue of cavitation.
On the assignment that's just posted on Blackboard, homework 6, there's a problem where instead of giving you the equation for a system curve, the pump curve, instead of giving you an equation, I give you a figure. And so the system curve is an equation, but what you're going to need to do is create an equation given the image that's provided so that you can solve for Q. So in other words, you're going to have to digitize this figure. And by digitize, what I mean is, if you create a table on Excel where you say for a certain flow rate, what is the head that's being added. So you can see, for example, I've said for a flow rate of 0, the head is 200. For a flow rate of, I don't know why I went, okay, so 20 CFS, you can see the pump head is 150. My recommendation would be, instead of going all the way up to 20, maybe do it in increments of like 5, 10, 15, and so on. So at 5 CFS, it's still probably pretty high. You're going to have to take a straight edge or, do it electronically and find out, for when you send up a vertical line and reflect it off of the curve, what is the head that you've got for a certain flow rate. So at 5, it's maybe 190 feet of head. So you'll do that several different times, and then in this third column, you're creating a guess of what is the pump head being added based on the form of this equation. So the form of a pump equation is that there's some intercept, so 200 is the intercept, minus a coefficient times the flow rate squared. So the big unknown is, what is the coefficient that you should use for a best fit between all of the data that you observe and your attempt to replicate it with digitizing the curve. So in other words, you're going to have a known pump head that you read off of the figure, and then a predicted pump head based on some C value. So, maybe C is 0.1, maybe C is 0.2. And so have this data based on an equation which is referring to some C value, and then you're going to do a goal seek where you're trying to minimize the difference. So in other words, if your data is here, like you've got these data points, and then if you had C equals 0.5, then maybe the curve would look like that. That's no good. Maybe if you did C equals 0.25, your curve would look like that, so it's too low. So you're going to play around with what is the C value that matches up with the data. Maybe the data is more like this or something, but you're going to try and minimize the difference between the known pump head and the estimated pump head based on some coefficient. So once you have that figure digitized, then you can set the pump curve equal to the system curve. So the first step really is just digitizing the data. And I've given you some instructions on the handout PDF that goes along with that assignment, but I also wanted to introduce it in class now. So any questions before we move on from this tip? Okay. Last time we talked about the efficiency of a pump combined with an electric motor. You saw that in the video that we watched that there can be different impeller diameters, that there can be different impeller thicknesses, that there's a wide range of factors that can affect how a pump performs. And pump manufacturers have developed figures which kind of summarize the performance of a pump or series of pumps that are closely related. So you can see that this is a figure that was put together by Gould's Pump Incorporated. I have no idea if they're still in business. This figure comes from 1987, so it could go either way. But some of the things I wanted to share with you on this figure, now this has, similar to what we've seen before, on the horizontal axis is capacity, meaning flow rate. So if you look at the units, we've got both cubic meters per hour on the figure and then also gallons per minute. So we could use the same figure whether we want SI or traditional units. And then on the vertical axis, head is in feet on the left-hand side, or on the right-hand side, head is in terms of meters. So again, you could use this figure potentially for either sets of units. Now notice the curvature of this figure, which is similar to that video we watched where it was showing the pipe which was at first horizontal and there was a really high flow rate because there wasn't any head that the pump was working against. But as you inclined the pipe and the pump is having to work against some load and create additional pressure, then the flow rate decreases. So the shape of this curve follows that same trend that was observed and demonstrated in the video of you have a cutoff head, which is the amount of head or pressure that is going to cause a flow rate of 0. But then if the pump isn't having to add that much pressure, then it can actually move the water through the system and generate a positive flow rate. So as the flow rate increases, the head that it's adding to the system decreases. So that's the first trend I wanted to share with you. The other thing, though, is that for the same pump, it's going to perform differently depending on its rotational rate. So you'll notice here is 3,600 RPM, here's 3,200 RPM, 2,800 RPM. So you could match a given pump with a motor that has a rotational rate of 2,800 RPM, and then those paired together, it would be generating about 280 feet of cutoff head. Whereas if you put it together with a larger motor, which is rotating faster, at 3,200 RPM, the same pump, where we're not changing any of the internal characteristics, we're just driving the shaft faster, is now going to generate about 365 feet of head instead. So rotational rate is one of the factors that affects the pump performance. Another thing that's interesting on this figure is these curves where you can see where it says 50, 55, 60, 63. Anybody guess what those numbers are referring to? It's just a guess, so there's no reason to be shy. No reason to be embarrassed if you don't get it right. It's efficiency. So a certain pump is not going to have the same efficiency across a large range of operating characteristics. And so, for example, if we have a pump that we're driving at 3,200 RPM, if it is pumping a flow rate of 160 gallons per minute, then it's intersecting here, you can see the 50% efficiency. It's more efficient, it's 55% efficient when it's operating at 190 gallons per minute. And its maximum efficiency for that rotational rate of 3,200 RPM, its maximum efficiency is 65%, and so it's going to be most efficient at translating mechanical energy into fluid energy here at the flow rate of, it looks like, about 360 gallons per minute. So the efficiency of the pump is something that we can get off of the figure. And then one last thing I want to show you here is NPSH. And that stands for net positive suction head. And that is a statistic that gives you some information about the risk of cavitation. Cavitation is something that can cause damage to equipment, and we're going to talk in more detail about how you can calculate the risk of cavitation. But one of the factors that you have to know about a pump is what is the net positive suction head required. So NPSH-R is what we're talking about here. It's the amount of suction head that is required by a pump to prevent cavitation. And so that's something that every pump is going to be slightly different. You can get the information from the pump manufacturer and then do the calculation if cavitation is at risk. Any questions about this figure before we move on and talk more about cavitation risk? Okay, so this is a kettle of boiling water. And of course, as we all know, at sea level, water boils at 100 degrees Celsius. But water doesn't boil at 100 degrees Celsius at other altitudes. For instance, at the top of Mount Everest, water boils at 69 degrees Celsius. So what do you know about Mount Everest compared to here? What are some differences between Mount Everest and sea level? Lower pressure of what? You're right, lower pressure. Atmosphere, right. So why would water boil at a lower temperature when it has less atmospheric pressure? That's what we should be asking ourselves. What it relates to is that when you've got water and it's open to the atmosphere, water molecules are trying to go into the vapor phase to some extent. There's something called a vapor pressure, P sub V, which is related to the kinetic energy of the water molecules that are in the water, and whether they have enough energy, a certain fraction of the particles will have enough energy to go from a liquid to a gas. And the atmosphere is pushing back at any given time. And so when you are heating up water, you increase the vapor pressure up to the point when the vapor pressure is equal to the atmospheric pressure, the water begins to boil. And by the way, like the little bubbles that we see in the water here, those aren't air bubbles. It's not like that's 80% nitrogen, 20% oxygen, 1% carbon dioxide. It's not air. That is water vapor. So it's H2O. So what's happening when you heat the water is you're increasing the vapor pressure until the point at which the average kinetic energy of the particles in the water is enough that it can start going into the gas phase. So vapor pressure is this property of the pressure at which a liquid will boil. And it varies as a function of temperature. Vapor pressure goes up when temperature increases. Yes, you won't find this in the notes. This was a late addition. After our class on Monday, when I got a few blank stares when we were talking about cavitation, I thought I probably needed to add some additional information about like where cavitation comes from. So cavitation at its source is a phenomena that's related to vapor pressure. So vapor pressure, every liquid has a different vapor pressure. For example, alcohol, you probably already know alcohol evaporates more quickly than water at a given temperature. So the vapor pressure of alcohol is higher than water. Or oil has a lower vapor pressure than water. So every liquid has a different vapor pressure at a given temperature. But for a given liquid, as temperature goes up, so does the vapor pressure. So here is some data for water. And probably if you remember back to chemistry class, you remember there's some special significance about 760 millimeters of mercury. You know, that's atmospheric pressure, 760 millimeters of mercury. So they defined the temperature scale of 100 degrees Celsius is the boiling point of water. Like they said, by definition, 100 is the temperature that water boils at. And it just so happens that when water is at that temperature, it's exerting a pressure of 760 millimeters of mercury. The liquid molecules are trying to escape from the liquid phase into the vapor phase, and it has an equal pressure to atmospheric. So here we can graph it. It's not linear. The vapor pressure of water is non-linear. So how does this matter about cavitation? We're talking about pumps, right? And how does pumps and boiling water relate? Do you remember at all in the fluid mechanics lab, one of the labs that you worked on was the Bernoulli's lab, and I think you looked at a venturi where water was flowing pretty slowly at a low velocity, and then it went through a throat that was narrower and it had high velocity. Do you remember that lab that I'm talking about where it had the little tubes coming up and you maybe traced with a pencil the shape of the piezometric pressure at different points? What do you remember about the pressure at the throat compared to the pressure before the pipe contracted? How did the pressure change when the velocity went up through that throat? Pressure was lower, right? So high velocity, low pressure. Low velocity, higher pressure. If Dr. Yoon had really let you crank that thing, like really just put lots and lots of water through that venturi, what you'd find is that there's a certain velocity that's so high that it causes a really low pressure of the water. And in fact, if the pressure in the throat of a venturi gets low enough, then you can start to see little vapor bubbles form. Cavitation can form. And the critical threshold is if the pressure in this throat gets below the vapor pressure, then that's when cavitation forms. So for example, when you were in the lab, it was probably about 20 degrees Celsius. So the water was about 20 degrees Celsius. So this pressure that it's talking about here is the pressure, absolute pressure. Not gauge pressure, but you know, in the lab, it's probably 100 kilopascals, or you know, about 750 millimeters of mercury in the lab. So if the absolute pressure of the water in the venturi got below the vapor pressure, then it would begin to boil. Not because it's hot, but because the atmospheric pressure that's resisting the vapor pressure is equal. So you can get water to boil by raising the temperature, or you can get water to boil by reducing the pressure. Either one will cause the same effect. Frankly, I don't remember what this video is, but I'm intrigued. Let's take a look. Oh, you gotta watch the commercial first, though. Grammarly. Did you know Grammarly is free for Marshall students? Yeah, who needs Grammarly, though, when you've got ChatGPT, right? So, all right, so this demo is basically just showing that you can get water to boil either by heating it up, or what this person is doing is vacuuming out all of the water in a glass bell. And so I'm sorry, not vacuuming out the water, vacuuming out the air. And so by sucking all of the air out, the water is cavitating. So you see all these little vapor bubbles that are forming here? That's because, and then he's making the point that it's not cooked, even though the water was boiling. You know, to cook the noodles, the water would need to be warm, but all that was happening was that some of the water was going into the void above the container because the pressure of the atmosphere surrounding the water was lower than the vapor pressure of the liquid. Okay, so now we've talked a little bit about vapor pressure, and here's just another look of the data, this time in terms of newtons per meter squared, which is more useful to us. That's usually the units that we're working with in pressure traditionally in the SI units. Yes?
Just speaking of tables, you had mentioned that there was a table error in the textbook.
Yeah.
Do you happen to remember what that is?
Yeah, let's go back to that because I think I mentioned it in one of the slides here. It was related to the bulk modulus of elasticity for water. And so the error in that table 2.3 is that they say it's the bulk modulus divided by 10 to the 9th, but really it's this number times 10 to the 9th is what gives you the bulk modulus. So I think what I was looking for in that assignment where you had to look up the bulk modulus is, you know, the pressure of the water is just at this standard range, 20 degrees Celsius. So I was hoping that you'd use the bulk modulus of 2.07 times 10 to the 9th. So that's the figure that's wrong in our book. Okay, so let's talk about cavitation. Now we all recognize that low pressure can cause boiling. So there's lots of ways that you can experience low pressure. You can experience low pressure by getting a vacuum pump and sucking all of the air out of a system. That causes low pressure. Or the venturi that we're talking about where you have a contracting pipe section. Sometimes they see low pressure. Did I show you some pictures of a dam in California that was all broken up? Yeah. Okay. They had low pressure at the bottom of the spillway because the water, as it went down that spillway, the velocity got really high as the water is going down that spillway. And so there was a section of water in contact with the spillway that had a high velocity and therefore low pressure. Another place that you can have low pressure is in the suction side of a pump because the water has a pressure of 0 at the interface of the atmosphere and the water. So at this location right here, it's just 0 gauge. Now pressure is increasing when you go down. Then when you go into the pipe, the pressure is decreasing in the direction of flow. So the pressure is getting lower and lower and lower. And so what potentially can happen is that if this suction side pipe is long enough, or if there's a big vertical deflection, like if the water level is really low and you're having to lift the water before it goes into the pump, then you can have a location of really low pressure where cavitation could form on the impeller blades. Because remember, high velocity, low pressure, you've got a high velocity moving blade inside of the pump, and because it's moving at a high velocity, it on the downstream, on the suction side of the impeller, the pressure is very low. Now, on the pressure side, once the water gets through the pump, the pressure is high again. But if any bubbles form on the suction side of the pump, then the bubbles, once they get to the pressure side of the pump, will collapse and send little shock waves through the pump, and that can cause damage, pitting to the pump and to the impeller blades. And like if the blades get eroded and it's imbalanced, it can start to vibrate. And there have been big industrial accidents. There was a notable one in Russia in, I think, 2006. They had a big hydroelectric facility that basically exploded because one of the impellers that was at this hydroelectric facility that was supposed to be generating electricity, there was some cavitation that occurred. It got out of balance and it just started to wobble until basically the entire building that this impeller was in, it got completely destroyed. So cavitation usually doesn't have huge acute consequences like that where it all comes together with a bang. Usually it's just a gradual erosion and breakdown of your equipment. But we try and avoid cavitation for that reason, just because of the damage it can do. It can cause localized pressures of up to 800 megapascals, which is really high. So this is showing some of the pitting and the damage. It's not chemical attack that's caused this. It's just that these little vapor bubbles were formed and collapsed on the impeller blade. Okay, so to prevent all of that, we have to know about the difference between how much pump head is required by the pump and how much net positive suction head is available in the system. And so you can calculate the available net positive suction head by starting with the atmospheric pressure divided by the unit weight of water. So P naught is just the pressure of the atmosphere at whatever your location is. And by the way, all of these calculations are done in absolute pressure. Oftentimes we'll do our calculations in gauge pressure, but cavitation calculations are done in absolute terms because that's what we have for vapor pressure. Vapor pressure is on the absolute pressure scale. So we want to know the absolute atmospheric pressure. Then you'd subtract out the elevation head difference between the water elevation and the location of the pump. So Z sub S would simply be the distance between the water and the pump. So how far apart, how far does the water have to be lifted vertically up is the delta ZS. Now H sub L on the suction side is the cumulative friction and local losses, but only on the suction side of the pump, because it doesn't matter what's going on upstream, after the pump. It only matters what happens between where the water's getting started and the pump. So it's just the suction side. And then you also subtract out the vapor pressure of the water. So that will tell you how much is available, and then what you do is compare it to the required net positive suction head, and if the available is greater than what's required, then there won't be cavitation. But the required suction head increases with increasing flow rate. So if we go back to this figure, you'll notice that a certain pump is going to require only this one, 8 feet of suction head is required when it's operating at a flow rate of 225 gallons per minute. But when it's operating at 550 gallons per minute, it needs 30 feet of suction head. So the question is there that much suction head that's available? Because if not, it's going to cavitate. So the risk of cavitation increases the faster the pump is operating. As you put more water through the pump at a higher flow rate, then the velocities, the liquid velocities in the pump are higher, and therefore the pressure on the suction side of the pump is lower. And then the decision criteria of whether you're at risk of cavitation is if the net positive suction head required is greater than what's available, then cavitation occurs. And then the flip side of that is if what's available exceeds what is required, then cavitation will not occur. There is this phrase called incipient cavitation, and it means that you're just right on the verge. So when the two are equal, then that's a limit that sometimes is calculated. Is, for example, you could be looking at a physical situation and you could say how far the liquid level can fall on the suction side before there's a risk of cavitation. Or you could say, what's the maximum length of the suction head pipe that's going to cause a certain amount of head loss that could cause cavitation. So when you're doing that kind of analysis, what you do is you'll set the required suction head equal to the right-hand side of this equation, and then solve either for, the delta Z or the unknown head loss quantity, or sometimes even you're calculating what's the vapor pressure that's going to cause cavitation. So if you look, all of these three terms after the atmospheric are subtracted. So a big delta Z gets you closer to cavitation, more head loss gets you closer to cavitation, and then a larger vapor pressure gets you closer to cavitation. And so remember what we've learned about temperature. What's more risky for cavitation, warm water or cold water? Warm water, that's right. And it's more risky for cavitation because the vapor pressure is higher for warm water, and therefore this last term is going to take away from the atmospheric term more strongly if the vapor pressure is high. Okay, so I'm showing you a system here. We've got a system where we are pumping water from a lower reservoir to an upper reservoir, and the only dimensioning that we're given is the one that we need. The dimension that there's 4.3 meters of elevation difference between the water on the suction side and the physical pump itself. We don't need to know what's the overall delta Z. We just need to know the delta Z on the suction side, so between the pump and where the water's coming from. And let's just say that from the flow rate that is known, we calculated the head loss in terms of, keeping track of both the local and the friction losses, and combined it's 1.6 meters. And then if we look at the fluid properties, let's say this is 40 degrees Celsius water with a certain vapor pressure and a certain unit weight of water at that temperature. And then for this example, let's assume that the water, this is at sea level, and so the water is working against an atmospheric pressure of 101,325 pascals. So P naught is 101,325 pascals. So what I'd like you to calculate is, will cavitation occur? So remember, what you're going to have to do is first calculate NPSHA, and then compare to NPSHR. So available we get from the system, required we got from the pump manufacturer. So the required suction head for this pump is 3.5 meters, but what's available is 3.76 meters. So if we start with the atmospheric pressure and divide it by the fluid's unit weight, and then subtract out the elevation difference on the suction side, the head losses only on the suction side, and the effect of the vapor pressure, the available is above what's required, and so it's not going to cavitate. Okay. Now, in a real-world situation, how would this kind of problem be different? Well, you wouldn't just be given the head loss, of course. That's something that you'd have to calculate, and you wouldn't just be given the required NPSH. That's something that you'd have to look up off of the table. And then the other thing that you should ask in a situation like this is, so how far away are we from cavitating? We're pretty close, actually. Our available amount is 3.76 meters, and the required is 3.5. So how much further can the water level fall in the source tank before cavitation occurs? Another 0.2 meters. So if the water level falls more than like about a foot, then cavitation is going to start in the pump. So this is actually kind of a risky situation. So how could we reduce the risk of cavitation? Well, it's mostly here the delta Z. So what we could do is we could lower the pump You see how there's this big vertical height and then it starts flowing horizontally? All we'd need to do is just lower the pump down to the water level, and that would eliminate a lot of that risk for cavitation. So that would be one thing that could be done, is just lowering the pump. And of course, the pump, like the pressure side, is going to have to be longer, but we're not worried about cavitation on the pressure side. It only sets up on the suction side. So the number one thing you can do is lower the pump. The other thing is that you could increase the diameter of the suction tube. So the pipe that's drawing the water into the pump, if you make the diameter bigger, then there's going to be less head loss. So you could reduce the head loss, you could reduce the delta Z, or I guess we could cool off the water, but that's probably going to have the relatively minor effect. It would be not practical to cool off the water as a way of preventing cavitation. The number one thing would just be to make sure that the pump isn't so high, to try and lower it. Any questions before we move on? Okay, so let's get some more experience with pump operations and finding the operating point. Let's say that, boy, this slide's a mess. There's just so many equations on here. Okay, let's say that we're given a pump curve, and to make things simple, to make the system curve. So here's the general form of the system curve. You're given the F, the pipe length, we know the diameter, the delta Z you can see is 12 feet. There's just one K, so a K value of 1. So use the data from the figure and what's given here to set up the system curve, and then set it equal to the pump curve. And let me write the steps on the board here. First, we're going to find the operating point. So solve for Q, set system curve equal to pump curve. Solve for Q. And then it's asking, how long will it take to pump 1 metric ton of water? Does anybody know what 1 metric ton is?
2,200 pounds. No.
A ton for like traditional units is 2,000 pounds. It's 1,000 kilograms in 1,000 kilograms. And so, 1 metric ton is 1,000 kilograms. So in other words, what we're saying is 1,000 liters. So we want to find out, basically, solving for the flow rate, at that flow rate, how long would it take to pump 1,000 liters? And then we'll take efficiency into account. If the pump is 80% efficient and the motor is 65% efficient, we're going to need to calculate an overall efficiency and then put it into the power equation. So I guess we're going to solve for the overall efficiency and then put into the power equation. All right, so first things first, you're given the pump curve, and so create the system curve with the length of 135 meters, the F value that's given, the diameter that's given. I guess just to save you a bit of time, I'll tell you the cross-sectional area of the pipe here. The area of the pipe is 0.04909 square meters. All right, so I'll pause while you start on those calculations. I'm afraid that probably you're not going to be able to get through all those calculations, so let me just show you a little bit about where things are headed. And so we're given a pump curve, and we need to create a system curve. Now, it looks like when I created this example, I was making a little bit fussy by including the velocity head at location 2. So if you apply just this formula, you're not going to add the velocity head at location 2. It's not going to change much. The equation that I came up with for the system curve is 12, which is the elevation difference, plus 282.1 q squared. And I think it would just be 281 if you neglect the velocity head. Well, it would be a bit lower if you neglect the velocity head, but that's a relatively minor part of it. So when you, overall structure of the solution is that you set the pump curve and the system curve equal to each other, and you find the operating point, so a certain flow rate. So here, for a flow rate of 0.144 cubic meters per second, then I've calculated how much pump head is being added. So it's adding 17.85 meters of head to the system. And then as to how long it would take to pump a cubic meter, that would be around 7 seconds, so 6.9 seconds. Then the last thing that I took into account is the overall system efficiency of 52% is what's going to go in the denominator of the power equation, which has the flow rate, the unit weight of the water, and the pump head.